So now we're going to move on to two perspectives, ostensibly from the CEDAR-oriented community and then from the GEM-oriented community. So we're going to hear some words and some thoughts from Tom Immel.
All right, thanks Dave for that introduction, and thanks Josh and Jeff for providing us an update on introduction to the CEDAR document. The latest I've used that CEDAR document to sort of guide some of this presentation, particularly the aspects of system science. Short outline, I don't usually do this, but why not? How do you represent a system? I've got one complex historical example that, of course, I did not do, and then a simpler example which I've worked on to bring myself up to speed on what system science really might mean and to work through the aspects of that definition, if it's defined. And then talk about possibly a GEM CEDAR system diagram, or give one example of what that might look like. And again, it's open to discussion of what really our system might be. And then talk about briefly where do we go from here. So this is the Brotherton diagram of Brotherton diagrams. This is the one that was published as the in '86 as part of the advisory council workshop that the earth science community supported at NASA. This advisory council structure is not functioning for the particular disciplines at NASA anymore, but back then, Francis Brotherton, who was then or was soon to be the director of NCAR, chaired this committee. This is the same picture that Dave Heisel showed, except in much more detail. Now the arrows, every single arrow describes a connection between two systems and why it's connected. But again, it's simple, and this is hard to read, but it's powerful in its complexity and its simplicity. For this, in the simplest view, there's three boxes. Well, in the simplest view, there's two boxes. There's the climate system and biogeochemistry at the bottom, and they're connected in a number of ways. The climate system entails the terrestrial surface, the oceans, and the atmosphere. And here, this is atmospheric physics. These are connected to terrestrial ecosystems, marine biogeochemistry, and tropospheric chemistry. And you might be happy to know that there's an extra box over here that contains stratosphere and mesosphere that connects those two systems, as well as a number of other processes. Now I thought this sort of representation, and any representation of the Brotherton diagram sort of fits well with sort of a GEM box on the top, and a CEDAR box on the bottom, or vice versa, however you think of things. And so I went after this problem a little bit, trying to do the diagram. And this is not an easy diagram to draw between our two fields. You might argue that it's harder for a number of reasons. The regimes of plasma density and the scales that we're all interested in and so forth are really mixed up. And I was having trouble drawing that diagram. So I was complaining to my colleague Scott about that, and he says, why don't you start with something simpler? Well, I've never done this before. Like a kid and a hamster, maybe. That's a nice system. He says, that sounds just about your speed, Immel. So good. Well, give me a picture of a hamster. So the system I started with is to learn about what a system actually might be, is the human hamster system. And hang on, because I'm going to talk about hamsters quite a bit. This exhibits complexity as defined by the CEDAR document. I had that open as I was doing these slides, working through chapter 3 of that document, because this was really my primer on the aspects of the physical effects or processes that would be involved in a system. And I finished this pretty quickly. It wasn't too hard. Think of what a hamster needs and what a human needs and what they give to each other. A hamster, a healthy, vital hamster in a cage, where we usually find them, needs stimulation, nourishment, needs activity, like all mammals, and it could use a clean cage. The human provides that clean cage. It provides activity, hamster wheel and so forth. It feeds it, and if you can convince it that it's a good idea, that it wants, it being the human, that it really likes to keep the hamster going, it will actually clean its cage. What the human gets from this interaction is intellectual stimulation, sometimes the first close interaction of a human with a different life form. And it gets emotional stimulation of its emotions by just the fact that this is a completely adorable thing. And we're trained to like things that are adorable and attach to them and exhibit affection and to nurture them. That's a human instinct to nurture other beings. So these can feed back into the resources that are available to the human through its work, possibly through chores and an allowance, to provide to spare time for the interaction, and to feed, to find resources to feed, and even to clean the cage. But children don't want to do that, and so the hamster, it helps that the hamster is providing a feedback in the system, that it helps that the hamster is pushing the emotions of the human to do things that it normally wouldn't do. And particularly this nonlinear response, humans have a nonlinear emotional system. It's a small input in a human emotion system can produce a large response that lasts a long time. The hamster, in a symbiotic relation with a human, takes advantage of that to get everything that it needs for a good period of time. So what you end up doing, though, with these system diagrams is you keep having to describe what you actually mean. And so I think that's sort of a limitation of the system diagram, looking back at the original Brotherton diagram. And I'll talk about that a little bit more. You end up having to provide ancillary information to describe what you're really talking about. The interest of a adolescent human in practically anything usually starts very high and usually craters within a time period, probably, depending on what you're trying to maintain some interest in, 3 weeks to about 3 seconds. The hamster, this would be disastrous for a hamster that's in the care of a human. And so the combination of feedback and linear response of the hamster-human system maintains an environment and the interest in the hamster that the hamster requires of the human. There's also, feedback and nonlinear responses are part of system science. Preconditioning, we talked about this in terms of the magnetosphere, in terms of ionospheric response to magnetospheric inputs. It goes along, here's an example of preconditioning in the human hamster system. Interest in hamsters, I propose, starts high early in the age of a human and then crosses the threshold of disinterest into active anti-interest in hamsters. For instance, and real quick, raise your hand if you own a hamster. Well, keep your hand up if you have children. Yeah. Raise your hand if you have a dog. Thank you. So different mammals have a different curve here, a different slope and a different curve. And for hamsters, this is the age of the owner is important. It's not to say that if you weren't given a hamster that emotional response wouldn't take over, but the initial preconditioning of the system is very not conducive to the life of a hamster. The y-intercept of this curve, and possibly the slope, are affected by memory effects, like have you ever been bitten by a hamster? I've been bitten by a hamster. I really never want to see one again. But that pushes this curve around, which has, again, preconditions the system. And then the last question is, how long has this child been asking for a hamster? So imagine being asked for a hamster every day for a year and a half. And then finally, the kid gets a hamster. The nonlinear response to the finally being given a hamster is something like as nonlinear as spread F. So it has all these properties, this system, the simplest system you can think of, really. The sort of the buzzword that comes with it is, does the system exhibit emergent behavior? I mean, this is sort of the key to this, and this is something in our CEDAR book where we actually sort of hedge our bets on what's really an emergent behavior, because I think it's probably what you define it as. But I think that the human hamster system exhibits a lot of emergent behavior. This human is wearing a hamster shirt. This hamster is celebrating his first birthday. This hamster is a reindeer. This hamster lives in a mansion. This hamster has a bird for a friend. These hamsters are dressed as human babies. This young man famously declared his love for hamsters with a live studio audience. And these hamsters are wearing party hats. So I think there's a lot of emergent behavior in this system that we would have to compare ourselves against if we think we actually have good examples. So, a little more seriously, what did I find out in this exercise? Well, system diagram is limited. It's difficult to represent time dependence. You really need to fall back to some plots, either that come from naturally from the system that you're trying to describe, but maybe needed to actually describe what you're talking about, go beyond that diagram. Actual effects of feedback are left to the reader to guess. We have these big loops, but what does that really mean? Well, it means that the hamster, in the hamster case, lives a long time. A limited hierarchy of representation type mixes weak and strong drivers together. This goes back really to the Brotherton diagram, where you have ozone and NO and water vapor going some direction into some part of the system. Well, one of those is probably more important than the other, but you don't get any of that information from the diagram. And complexity involved preconditioning, memory, instability, we really have to describe that separate from the system diagram. But the strength of the system diagram is it allows one to convey important aspects of a dynamic system to a wide audience. I think we're not earth scientists, but you see the Brotherton diagram in a simpler, complex form, and you can start to get to feel what's going on there, what's important, and why people are studying that system. It reduces the system components that can be identified or focused for focused study, such as CEDAR-GEM or different aspects of the important scientific studies that we take on. And correctly done, it could be an enduring statement and a signature of the level of knowledge of a field. So I think what I have next is my first shot at a CEDAR-GEM diagram based on some of the recent important findings, which I'll get to in a little bit. But what we've seen early in this week is that ion outflow is a very strong coupling agent between the magnetosphere. What this is going to be GEM, this is going to be CEDAR. And the ion outflow is driven by a number of different processes that come from both the magnetosphere and the ionosphere. I guess I shouldn't go into too much. I can spend the rest of my time on this diagram. It's not perfect, and it is the system that I've defined. There's other ways to define the system. But if you settle on one thing that you find very important and want to focus upon, you can actually get from here to there with, what I've tried to take was Brotherton's approach of sort of having three boxes. Magnetospheric convection, magnetospheric particle populations, magnetospheric dynamics, compared to thermospheric dynamics, ionospheric density, and ionospheric flow. And everything else, and that basis, you can build upon pretty readily, I think, to show that, maybe not convincingly yet, that ion outflow, and what I need to do is connect my dynamo fields over to currents and so forth. But I think you get the picture that it's possible to get from here to there, and I think make a compelling diagram for our community. The system exhibits preconditioning, just as I think I mentioned this before. Preconditioning and memory in the system is believed responsible for susceptibility, for example, of the magnetosphere-ionosphere system in their coupling to produce DST this is a canonical DST storm from Comete et al. Paper, and then the two-step DST reduction in some storms is likely due to preconditioning from the first storm and the amount of ionospheric plasma that's out there when the next solar wind disturbance arrives at Earth. We have nonlinear responses of the cross-polar cap potential to the imposed potential in the solar wind. I couldn't use the internet here. I was trying to download this. There's a recent abstract I read of Joe Borofsky and company where they compared 9 different explanations for this nonlinear response. I wouldn't be surprised if some of that has to do with the ionosphere-magnetosphere coupling. But I need to get that paper and read it. Do we have emergent behavior? There's some recent examples, I think, that some people might point to or you might be thinking of. For instance, the recent science paper where, I took this slide from Bill Lotko's presentation on Monday, showing the fact that with and without ion outflow, the magnetospheric response to solar wind inputs is quite different. And with outflow, you get these sawtooth events that you don't, but without, you don't. Is this an emergent behavior? These really large, surprisingly large plumes of structured plasma that leave mid-latitudes and head towards the cusp and into and feed ion outflow. Is this emergent behavior where the humans are driving change, at least in part, changes in the upper atmosphere due to the addition of CO2 with a long-term change in thermospheric densities? Or is this emergent behavior where you have a tropospheric coupling up into the ionosphere and now, as we know, probably into the plasmasphere and beyond? Where I'm showing a plot showing the correspondence between an ionospheric index and the El Nino index. Well, whatever example you're thinking of, you've got to do better than a hamster in a party hat. So this is an acid test. If you're going to say something that is emergent, you have real emergent behavior, it better be it's hard to beat life for emergent behavior, but simple life, I think you should be able to get somewhere. And you have to have a convincing argument. So where do we go from here? I think this is just short. I think this is a good session. I think we should share and discuss our views on the systems view in the next weeks and months. Contributions to the systems diagram, any interest you have in that, I'm interested in, because I'm trying to actually put something together we could work with in the future. And please damp your nonlinear emotional responses to all this systems behavior. You may start ending up with developing your own emergent behavior. Okay, that's it. Thank you.